So as you can see, obviously we are in week 6. Um, this week we are working on chapters 9 and 10. Week 7 next week is where we'll be working on chapters 11 and 4. And remember, next week is also when I will go back and reopen all older homeworks and quizzes that you will be able to work on them if you want. And you will have the chance of making up one of the previous exams if you so choose. So all of that is going to be next week. This week, you are working on chapters 9 and 10. So this is, obviously where we are getting into the next part of our statistical study, which is going to be talking about hypotheses testing, parameters, confidence intervals. And actually, chapter 11 is going to continue that discussion, but we're tying chapter 11 with chapter 4. So, those are our two smallest chapters that you guys will be working on. So a part of this will continue next week also. And so again, guys, you will have homework assignments in my stat lab. You will have quizzes and exam for this. Obviously, we are no longer doing any discussion posts or assignments in D2L. So you will not have any of that this week also. So you will see under your reading assignments here again. I've included links to the textbook pages and then the handouts that I have created. So you have that available under the reading assignment. And then for viewing, I've included the crash course statistics videos, and then I've actually given you a link to the multimedia library because for this, I actually work on homework problems more so than do a lecture for this. So there's not a lecture video for this, but again, you have some available in the multimedia library if you would like to take a look. But you will see I have included several different example videos over here that you can look through to kind of get an idea. But we'll work on some of these examples just to again make sure, if you wanted to ask me some questions while we're going through it, you have that chance, because later on, if you're just looking at the videos, you won't get a chance to ask me questions. So we'll work on some of these, but you can see there's quite a bunch of them here that will help you out. So that's going to be under the viewing section. Also, if you look at your textbook for chapters 9 and 10, at the end of each section, they have this little technology step-by-step, instructions, and it's based on different, hardware. So you can see they have instructions if you're using a TI-8384 calculator, Minitab. If you are using Excel, what you can do in Excel, StatCrunch. And this is kind of where we officially start using StatCrunch. So you can kind of see the instructions over here for confidence intervals. This one here is talking about if you were trying to determine a sample size, and you're going to see these at the end of each section. So, definitely make use of this. We are going to be working on Google Sheets. So kind of part of the Excel, but, since we don't have the Excel stat add in, or at least I don't have that at my end, I'm going to try and show it to you in Google Sheets of how I do this. So I've actually selected some examples that we can work on from these sections. So let's see, this is section 9.1, and I thought we could work on, and I've actually selected examples that have a lot of multiple parts to them. So, some of the big, long problems, and I think the first one I selected was this guy here. And the other thing that I have done is created these sort of templates, how we do for our in-class activities. So they're kind of similar to that. So these templates here, you will see are pre-designed, and of course, this information will change for each example. So some of this is just here from the previous time I used this, but just basically templates. So you will be able to take, if you, and you can see on the bottom tab, I've put the numbers, so which problems these guys come from. So this one you will see is 9.1.27. And in Excel, in StatLab, you will see it's right there at the top where it shows you this is the problem 9.1.27. So that's kind of how I've labeled these. So let's take a look at this example here, and then we'll see how to use that template in Google Sheets. So this example is talking about a random sample of 1,012 adults in a certain large country was asked, do you pretty much think televisions are a necessity or a luxury you could do without? So out of these 1,012 adults surveyed, 531 indicated that televisions are a luxury they could do without. So now based on this data, we're going to have these different questions. And you can see on the top, it tells us this is part of 1 out of 5. So you're going to have 5 parts to this question. That's basically what this tells us, right? So the first thing they're asking us to do is calculate the point estimate for the population proportion of adults in the country who believe that televisions are a luxury they could do without. So this information is given to us because they told us 531 individuals out of the 1,012 told us that this is, a luxury they can do without. So your point estimate, and you will see right here in the handout, guys, or the template that I've given you the formula. So that's the p hat, which is x divided by n. So the x is going to be the 531 people. And of course, we know the total survey was done for 1,012. So that's the information for the x divided by n. And literally, that's all I'm going to do here. But as I normally do, instead of typing in those numbers, I'm just going to click on the cells. So what's going to happen here when I click on the cell, obviously it will calculate the, and I'm going to delete that for a minute. It's going to calculate the point estimate for us, or the p hat value. So what's going to happen if I leave it the way it is, and when you start working on this example and your number changes, let's say you just had 500, you will see it will automatically change the calculation for you. So that's kind of what happens again when you use cells instead of typing the numbers themselves. So we had 531 out of 1,012. Okay, so that is the first part. And let's see how many decimal places do they want. They want 3 decimal places. So we had 5247. So since you're going out to 3 decimal places, this is your normal rounding rules, right? So the 7 will make the 4 go up, and we will end up with 0.525. And that's your point estimate. Okay, now, and I don't know if you guys have had a chance to read through any of this chapter or not, but when you are working with, confidence intervals, we have to verify that we are actually meeting the requirements of the confidence interval. So this is where we have to make sure our sample is random. We have to make sure that it's going to be 5% of the population. And the other one is where you have to make sure that this calculation of n times p hat times 1 minus p hat, the very last one on the bottom, that number is actually going to be larger than 10. So there are some requirements when you're working with these confidence intervals, and you will see with different examples, they're going to have you check. So they are actually telling us in the problem itself that this is a random sample, right? Because they told us this is a random sample of 1,012 adults. So this, you're not assuming because they're telling us, so you are going to be, it is stated to be random. And if it's not given to you, specifically in the language, then you may have to think about, can we assume if it's a random sample or not? So, obviously that will depend from problem to problem. And then, like I said, this is the value you are looking for over here. So the n times p hat times 1 minus p hat. And this calculation, again, I've included right over here. So this is what we're trying to check if this number is going to be equal to or at least greater than 10. Oh, Montserrat, give me. So this is only going to be viewing rights over here, guys, but you guys can make a copy of this. So let me share this link with you through chat. This is for the chapter 9 examples, as you can see. So here's the link for the chapter 9. So just make a copy of this, or if you want to download it to work on it as Excel. I'm not sure how this will look like once you download it to Excel, but I'm sure it should be okay. So yeah, go ahead and save this, guys, because you can use this on your exam. All right, so let's check for the n times p hat times 1 minus p hat. So this is where, again, I'm going to just use the cells instead of typing in the numbers. So my n value, of course, is the 1012. I'm going to multiply that with p hat, which is what we just calculated earlier. So the 0.5247, and I'm just going to leave it at 4 decimal places, times, and then in parentheses, I'm going to do 1 minus p hat. So of course, click on that cell one more time, close my parentheses. And we just want to make sure this number is 10 or greater than 10. And of course, you can see 252 point something, so big enough. So we will be able to say this number is, again, 3 decimal places. So 252 point, what will that be? 382. So that looks good. Which is, of course, greater than or equal to 10. So we're satisfying the second condition. Now for the third one, this is where we have to determine if the sample size is going to be less than or equal to 5% of the population. So this one here, we're going to say sample size. Now, guys, if you again go back to the problem, they're telling us we have a random sample of 1012 adults in a certain large country. So they're specifying it's a large country. So in this case, they're not telling us if our sample size is going to be less than or equal to 5% of the population size. So in this case, we are actually going to assume that our sample is less than 5% of the population size. And I'm mentioning this over here underneath our little calculation. So I am telling you, assume that the sample size is less than or equal to 5% of the population, because they're not really telling us what the population size is either. So that's not really something we can calculate. So that's why we are making that assumption. So go ahead and fill in all those spaces, and then that's your second step of verifying. Now we are getting into actually constructing our confidence interval. Now, the idea behind confidence interval is we want to know, that point estimate value that we got of 0.525, which, as a percentage would be approximately 52.5%, right? So the confidence interval is talking about how confident can we be that, if we were to keep repeating this experiment, so, we kept selecting different groups of people in this large country, and we kept asking them the same survey question, right? What do you think if televisions are a necessity or a luxury you can live without? How close would our result always come out to be to this 52.5%, right? So the confidence interval actually helps us decide, are we going to be 95? And, that's just a level of confidence, how accurate you can kind of think of it, or how close to that percentage we're going to be. And so this will tell us, you may have a margin of error because, each group is going to give you a different result. But can we say confidently that, they're still going to be close to that neighborhood of 52.5? So that's the confidence interval values we're trying to figure out. So they're telling us to construct and interpret a 95% confidence interval for the population proportion of adults in the country who believe that televisions are a luxury they can do without. So for this one, we will actually come back to our Google Sheets here. So as you can see, we have a 95% confidence interval. They're telling us that in the problem. Your confidence interval can be 90%, it can be 92, 93%, 97%, 99%. It can actually be lower than 90% also. Sometimes you'll see 87, 89% in there. So again, be careful. This one is 95%, but you will see different confidence levels in different examples. So 95% converted to a decimal is 0.95. So you have to actually calculate your alpha value, and alpha value is always going to be 1 minus whatever that confidence interval is. So of course, if you do 1 minus 0.95, you know that's going to give you 0.05. So that's your alpha value. The next one is we have to do alpha divided by 2. And the reason we are doing that, if it will let me show you, if you look at the, no, come back. If you look at the formula here, this is the formula for calculating your lower limit of the confidence interval and your upper limit of the confidence interval. So obviously you will notice that it's the same formula. The only difference is you have a minus sign here and a plus sign here. But one of the first things we have to calculate, because we already know the p hat value, the n value. So what we are actually building up to is calculating the z sub alpha divided by 2. And that's your z score right over there. So before we can get to the z score, we need to calculate this alpha divided by 2, which is what we're working on right now. So we've got our alpha. Obviously, then alpha divided by 2, I'm just going to click on that cell, divided by 2, and that will give you 0.025. Now, based on this, we need to calculate our z value. Now, I believe your textbook, I think, has a table on this. I know as I was looking through earlier, I saw that. There we go. So here you can see, this is a really neat little table. You've got the different levels of confidence. So 90, 95, 99 are the most common ones. You can see when we calculate their alpha divided by 2, what these will come out to be, depending on the confidence interval. And then they give you your critical values over here. Now, this same critical value can actually also be found through your normal distribution table. Hold on just a second. Let me see if I can find that. I actually didn't think about that before. Actually, I think it may be in your course shell here. I believe I've included that. So under my lab statistics, I have actually given you this formula and tables from our textbook. And if you click on that, towards the end is where we have all the tables in this. So this is binomial, random numbers. In which you would have learned how to use this table in the previous chapter. So what you have to actually do is, very quickly, our alpha value is 0.025. So that's what you're trying to find in the body of this table. So 0.025. There we go, 0.025 right over there. And basically the idea is you match it to what the z-score should be. So let's bring this down a little so we can actually see that. And so here we have our 0.025. And then you're just matching it to where your z-score is going to be. So you can see that matches to 1.9 on the left-hand side, and then on the top, it's going to be 6. And you don't have to worry about the negative number so much in this case, because here we're just trying to use this as a critical value, not as, what the actual z-score is above or below the mean. So you can see it comes out to be 1.96. So that's from the table. If you use this table over here in the textbook itself, then obviously you can see we still get the same value. And this should be something, again, I would write it down or use it as a cheat sheet when you're working on this section for the exam, especially for these 3 common level of confidence values. So those are the two ways you can calculate what your z-score is going to be. So 1.96. So this will always stay the same, guys, as long as you're doing the 95% confidence interval, right? Now we are ready to calculate our lower bound and upper bound. So for this, I'm basically going to, work on this little formula that you see with the minus sign. So equal to, you are doing p hat, which is going to be this number over here. Let's move this guy just a little bit. So p hat, then we are doing minus z sub alpha 2, which is that 1.96 value we just calculated. And then you're multiplying that with the square root of p hat times, we will be doing 1 minus p hat. Close that. So that's your numerator. And then we're dividing this by n, which is 1012. So again, you will see I am completely basing everything by using the cells instead of typing in the numbers, because again, when you guys go in and put in your x and n values, all of this should automatically be calculated for you. So that's our lower bound. Again, p hat minus z sub alpha 2, then multiply square root of p hat 1 times p 1 minus p hat, and then divide that whole thing by n. Now this is the same formula for the upper bound. The only difference is we are going to change the minus sign to a plus sign. So I'm literally just going to copy paste that formula, and right at the beginning, instead of that minus sign, I'm going to change it to a plus sign, and everything else will stay the same. And you can see that calculates your upper bound and lower bound for the 95% confidence interval. So what we are saying with this, guys, again, is that yes, you got 52.5 as your point estimate based on this one survey. If we were to repeat this same survey with different groups of people, we can be 95% confident that this 52.5 value can go actually from 49.39% to 55.555%. So you do have a little margin for change there, right? Because it can actually on the lower end go to 49.39%, and on the upper end it can go to 55.555%. So putting that into our little here, you will see they're giving you two options. They're telling you, is this a we are, of course, this will be 95% confidence, or is this a 95% probability? So which option would you choose, A or B? Are we 95% confidence, or is this a 95% probability? What are you trying to find? What was question part C asking us to find? Aren't we finding a confidence interval?
Would it be A, because 95% confidence interval?
Yeah, exactly. So look for that terminology, folks. Very nice, Lourdes. So since we know we're finding a 95% confidence interval, obviously you are going with, we are 95% confident. So be careful about that terminology. That's the easiest way to, figure this out. So we are 95% confident the proportion of adults in the country who believe that televisions are a luxury they can do without is going to be between, and let's see, they again wanted us to round this to 3 decimal places. So we had 0.4939. So again, that 9 will make the 3 go up. So 494. And then this will be 0. Since we have 55555, 55, and then the last 5 will make the, 1 in the third position go up. So 0.556. And you will leave these as decimals, guys. Do not convert them to percentage, okay? Even though I'm talking about them as percents, our answers will remain in decimals. Alrighty, so part D is actually talking about making sense of this, right? Making an understanding. So they are saying, is it possible that a supermajority, which would be more than 60% of the adults in the country, believe that the television is a luxury they can do without. So look at your confidence interval and tell me, do you think 60% of the adults in the country believe that television is a luxury they can do without? Yes or no? Because where is our confidence interval? From 0.49, 4, I think, to 0.556. 60% as a decimal would be 0.6. So looking at the confidence interval, is it possible that more than 60% of the adults in the country would say television is a luxury they can do without? And Pafuwa, I see you are shaking no as the answer. Because do you see 60% included in that confidence interval?
No.
Very good. Yeah, because it is beyond the limit of our confidence interval. We are only going basically, just from 49% to about 55%. So you do not have 0.6 included in this interval. So very nice. So what you're actually going to do for your answer here is you're going to say it is possible. Because, again, this is all based on estimates. It's possible, but not likely based on the results that we are seeing. So it's possible, but not likely that a supermajority of adults in the country believe television, is a luxury they can do without, because the 95% confidence interval does not contain, and put that in decimal format, 0.6 for that 60% that they're talking about. Now, this one over here is actually going in the other direction. So far we've been talking about people who said television is a luxury they can do without, but what if people said television is a necessity, that they must have it and they cannot live without it, right? So how would we calculate that confidence interval? So they are saying use part C, which is where we calculated the confidence interval. Use part C to construct a 95% confidence interval for the population of adults in the country who believe that televisions are a necessity. So that's actually that last part that you have here in your handout. So that is where I'm asking you to calculate this, because this is going the other way, right? People who think this is a necessity, you are going to do 1 minus the lower bound value, which was the 0.4939. And then for the upper bound, we will do 1 minus the upper bound value, which was the 55555. And this will give you the confidence interval for people who think television is a necessity, they have to have it. So of course, guys, the smaller number will be the lower bound. So that's 0.4445. So that will round up to 0.445. So 0.445 for the lower bound. And then of course, the upper bound is coming from the 5061. So rounded to 3 decimal places, that will become 0.506. So that's, basically how you are tackling this. So this has calculations and it's asking you to make sense of, your results. So how do you interpret your results? And that's going to be a big part of these calculations, right? Just doing the calculation is not enough. We have to know exactly what they mean also. Okay, so unfortunately, I don't have a whole lot of time to do too many examples from each section. So like I showed you under the viewing in D2L, I have several different examples that you can look through, but let's move on to the next section here and pick an example from the next section. Come on, buddy. There we go. Okay, 9.2. And we're actually going to work on number 12. So this is 9231. And you should see at the bottom again of this handout, on the 4th page, you have the 9231 template for this. So again, delete all these. Okay. Okay, so this one is talking about, and here actually the reason why I picked this example is, of course, you can see they're giving us a raw data instead of just, based on a survey like the previous question was. So this one is saying the following data represents the pH of rain for a random sample of 12 rain dates. The normal probability plot suggests the data could come from a population that is normally distributed. A box plot indicates there are no outliers. And then, of course, they're asking us to complete parts A through D. So this one has 4 parts to it. So the first thing I'm actually going to do is copy this data. So again, let me just show you what I'm doing. I go under this little copy tab over here, click on that, and I'm copying it to clipboard since I'm doing this in Google Sheets. So copy to clipboard, and then I actually do have to click Control-C on my keyboard to copy this data over. So it's already selected. All I have to do is click on Control-C, and then I'll come over here and I'll get to my little data box and I'll just paste it by using Control-V. So Control-C for copy, Control-V for pasting. Okay, so this one, of course, you can see we've got our calculations laid out, but that's the first thing they're asking us to do is determine the point estimate for the population mean. And in this calculation, your point estimate is a little bit different because that's actually going to be this X bar calculation. And as you can see, this is where, you're basically taking the mean if you think about this, because all you are doing is taking the total of the 12 rain dates, the rain values we have, the pH level, and dividing it by N. So you can use the formula or you can use the built-in function, which is, of course, as you know, going to be average. And then I'm going to select these 12 dates. And I'll do that just to show you that this also works with the formula. Remember, you can use the sum function to add up all of these. So that's my total, and then divide by 12 because we have 12 data values. So you will see you're going to get the exact same answer. So you can use the average built-in function or you can use the formula from your textbook. All right, so we've got that. And I think they said 2 decimal places to round it to. So this will, as you will see, become 5.07. So that's your point estimate. And one thing you should pay attention to is because you had the raw data here for the point estimate, we actually did the average calculation in the previous section. For point estimate, you just divided X by N, right? Because that was based on a survey. So different approaches when you have different values or data sets you're looking at. So be careful about that. All right, so now they're obviously asking us to construct our 95% confidence interval for the mean pH of water. So let's come back over here. So a few things that we will need to be able to calculate this confidence interval, is, again, if you look at these formulas down here. So this is going to be for our lower limit, upper limit. And of course, same thing, you will see they're the same formulas. The difference is a plus and minus sign. So we already have our X bar. We already calculated that. We are going to need to calculate now, instead of a z-score, we are actually doing a t distribution over here. So you have a t sub alpha over 2. We will need to calculate our S value. And of course, we already know N is going to be 12. So 2 numbers that we need to calculate is the t sub alpha divided by 2 and the S value, which is going to be your standard deviation. So again, you can use the built-in function that you want, or you can use the formula from your textbook, but obviously we're going to use the the standard deviation. Now you can do standard deviation or you can do standard deviation dot S, which is what I recommend because this is a random sample. This is not a population. So to get accurate result, guys, use the dot S function and then, obviously select all 12 of these data values here. And that is going to be your standard deviation. So, obviously make use of built-in functions, even if you're using Excel or Google Sheets. Now, another calculation that we are going to need is going to be this right over here. So N, of course, we know is 12 data values, and then your degrees of freedom that we talk about is actually going to be N minus 1. So degrees of freedom is always going to be whatever the N value is, subtract 1 from that, because you need that for the T distribution. And we'll talk about that here, when we calculate our T value. So keep that in mind. N minus 1 is your degrees of freedom. Now let's get down to, we are doing a 95% confidence interval. So same thing over here, guys, you will do 1 minus 0.95 to get your alpha value. Just like we did in the previous example, divide that alpha by 2 and you will get the alpha divided by 2 value. Now we need to calculate this T value over here. Ian, which sheet are you talking about for the T value?
Yeah, the one you're working on right now.
It's the same link that I sent you. It's just on the 4th page. So at the bottom, look for 9231.
Okay, sweet.
Okay, awesome. So let's find our T distribution table here. And this is again that same handout that's in D2L that I showed you before. And we're just scrolling down till we get to the T distribution table. There we go. So here's your T distribution. So you will see the way this table is set up. Our alpha divided by 2 values are right here on the top, and then your degrees of freedom are right here on the left-hand side. So we had, can't believe I forgot that number. I think 0.025. Yeah, so that's our alpha divided by 2, 0.025, and our degrees of freedom is 11. So 0.025, degrees of freedom 11. And looks like they meet right over here at 2.201. So everybody okay with how to use this table? Okay. So look for the alpha. So again, the top here is alpha divided by 2. Come on, buddy. Alpha divided by 2 here on the top, and then your degrees of freedom down here. All right, so 2.201. 2.201. Alrighty, so now we're ready to calculate our lower bound and our upper bound. So just going to follow the formula. You have X bar. Let's move this up a little. Oops. X bar, so just going to click on that cell, minus my T value, so 2.201, multiply that by standard deviation. We just calculated that. And then we're dividing it by square root of our N value, which is 12 right over here, right? So X bar minus T alpha sub 2 multiplied by S divided by square root of N. You have your upper bound. Again, just like I did before, I'm going to copy this formula for the upper bound, paste it, and then change that minus sign at the front to a plus sign, and that will give us our upper bound. There we go. So let's see what our rounding rules are over here. Obviously, guys, you are still calculating a 95% confidence interval, which means you are still going to say there is a 95% confidence that the population mean pH water will be between, and they want this to 2 decimal places. So that's going to be 4.81. Yeah, 4.81 and then 5.32, because that 9 will make the 1 go up. So 481 and 532. And here you will see, since we are talking in terms of the pH value, right? You didn't get 0 point something answers like we did in the previous example, because there we were talking in terms of population proportion, right? Which are percentages. Here we're actually talking about what the pH level will be. And so your numbers are going to be different over here. So just to kind of, see that contrast between your examples. Now, this one example is kind of interesting because we did the 95% confidence interval. So we got 481 and 532. Now they're saying what happens if we make that confidence interval even more higher. So now they're saying, okay, let's change that to a 99% confidence interval. So what's going to happen in the 99% confidence interval is your t-value is actually going to change, right? Because your alpha value is going to be different. So for this guy, we will be doing 1 minus 0.99 because we have a 99% confidence interval. Oh, instead of a minus sign, I put a decimal. That should be 1 minus. There we go. Then obviously that means our alpha divided by 2 value is going to be different. So 0.005. Your degrees of freedom obviously will still stay the same because we still have 12 data values. So degree of freedom is 11. But now our percentage has changed. So 0.005 and degrees of freedom 11. So 0.005 right here. Degrees of freedom 11. So where are they meeting? 3.106. So there you go, 3.106. So, again, honestly, most of your formula will stay the same. So if you wanted, you can do a copy paste from the 95% confidence interval, bring it here. But, obviously we will need to change the box for the t-value. So that is the B22. Instead of B22, that has to be E22. But everything else will stay the same because your X bar, S, and square root of n values are not going to change. And I'm going to copy that and paste it for the upper bound. And of course, in this case, you are just changing the minus sign to a plus sign. And make sure you still have that E22 for your t-value in there. And so notice how the upper bound and lower bound has changed between the 95% confidence interval and the 99% confidence interval. And you will notice this, and I'm sure they're going to ask you questions based on this also. When you actually change the level of confidence, your margin of error changes. So the smaller the level of confidence is going to be, the smaller the margin of error is going to be. The bigger the level of confidence is going to be, the bigger the margin of error. Because see, these numbers are bigger and smaller than this one. So you were at 4.8. This went down to 4.7. So that gap increased. This was at 5.3. This one has gone down to 5.4. So on both ends, that gap has actually increased in your level of confidence. And that's what happens. So let's see, 2 decimal places. This will be 4.71 and 5.42. So 471 and 542. This is still a confidence. 471, 5, and see, I already forgot that, 542. Okay, let's check that. And looking good. So this is where they're asking you what happens to the interval as the level of confidence is changed. Explain why this is a logical result. So as the level of confidence increases, the width of the interval also increase, because think about this on a number line. If this is, of course, 0 would be halfway through, and you would have, sorry, not 0, 5. If you kind of make that the midpoint, you have 4.81 here, 5.32 here. Now you're going to 4.71, which is of course going to be smaller than this. So 4.71 is going to be smaller than that. And then 5.42 is going to be bigger than that. So, this was your original interval. And as you can see, when we change that to 99%, that interval has increased. So that's kind of the comparison they're having you make here. So the width of the interval increases. This makes sense since we're not talking point estimate, we're not talking sample size, we are talking about margin of error, because your margin of error has increased, as I was trying to explain to you earlier. So confidence, the level of confidence increases, that means you're actually going to see more error. So your margin of error is also going to increase. And you should see, if you guys study polls and stuff in the newspaper, and they do polls about everything, about hobbies, what people like, the interests are, what's going on right now, politics, pop culture, whatever it might be. A lot of times under these polls, and USA Today loves to do these polls, all big newspapers do, but USA Today has a big cache of, different polls they do. But underneath that, you should always see what the margin of error for the poll is, because that tells you, what that confidence interval is, and based on that, what our margin of error there is. So, if they say 52% of the people are in favor of, whatever, let's say we're getting into an election year in favor of this candidate. So when they say 52% of the people are in favor of this candidate, there will be a margin of error, and it could be like 2.5% or something, which means from the 52%, you subtract the 2.5 or you add the 2.5 to get that confidence interval. So that's what the margin of error basically tells you. So this was from section 9.2. And again, we're not going to have time to do another example from this same section. I would like to at least do one example on hypotheses testing, because we've done confidence intervals over here. Chapter 10 is where we actually get into hypotheses testing. I'm trying to see what example do we have time to do. Let's do at least one from 10.1, and if we have time, we may do one from 10.2. So let me share the link with you from our 10.2 handout. Okay, so through the chat, you should see this link for the chapter 10 handout coming through. And I'm gonna have to clean this out. Okay, so let's do, oh, this is 10.2, not 10.1. Well, very quickly, let's do number 17 here. Okay, so this one is saying a soda can or a can of soda is labeled as containing 10 fluid ounces. The quality control manager wants to verify that the filling machine is not overfilling the cans. So, of course, they want to stay as close to those 10 fluid ounces as possible. They don't want to go over, possibly not even under. So in this case, we are talking about, what will be the average capacity, I guess, the average volume of the can of soda. So this is actually where you're going to use mu, because we're talking about an average as your symbol over here. And they are saying the quality control manager wants to verify that we are not overfilling the can. So we're not putting more than 10 fluid ounces. So you are actually going to say for the null hypotheses, we are going to say, and this H sub 0 represents the null hypothesis. So that's based on what the expectation is. And so we know the can of soda has to be 10 fluid ounces. So your null hypothesis will say the average weight or the average capacity of the can has to be 10. The manager wants to make sure we're not overfilling it, which means we want to make sure it is not going to be a number which is not 10. So for the null hypothesis, H sub 0, we're saying the average has to be 10. For the alternative hypothesis, which is the H sub 1, sometimes in some textbooks, they also use H sub A to represent the alternative hypothesis. So it can be A, or like your textbook does, it can be 1. And we're basically saying it does not have to be equal to 10. Oh, okay, so that did not work. So let me see again. We are saying the quality control manager wants to verify that the filling machine is not overfilling. Okay, so they do want us to use the greater than here because we are talking about not overfilling, which means we don't want it to be equal to 10. And that is something you really do have to pay attention to, because sometimes you do have to look at the way the question is written or the statement is written to see, do they want us to use not equal to, do they want us to use greater than or less than? So since they're saying overfilling, they do want to make sure it's not going to be greater than 10. So let's, yeah, see, and that's what it was. So since they're saying overfilling, that means they're saying it should not be greater than 10. So that's your null hypothesis. Now they are saying the quality control manager obtains a sample of 81 cans and measure the contents. The sample evidence leads the manager to reject the null hypotheses. So when you are rejecting the null hypotheses, and this is basically where we are saying you do not have, if you're rejecting the null hypotheses, we are basically saying that your machine is actually going to be out of calibration, because null hypotheses is saying you should always have an average of 10, right? The sample is leading the manager to reject the null hypotheses, which means that's telling him that the machine is actually filling more than 10 fluid ounces. So that's why there is sufficient evidence to conclude that the machine is out of calibration. Because, you know, when you're rejecting the null hypothesis, you're basically saying what you expect did not happen. So they're saying, suppose in fact the machine is not out of calibration. Now, this is something you will need to go and read the textbook for, guys, because you do have to understand how the type 1, type 2 errors have been defined. So what happens with type 1 error is basically you are saying you rejected the null hypotheses when you shouldn't have. And let's see if it will let me show you that chapter 10. 10.1. Because there's a nice little grid in your textbook over here. Yeah, so you can see here. So when you reject the null hypotheses, when the null hypothesis was actually true, that's when you lead into type 1 error. If your alternative hypothesis was true, but you still did not reject the null hypothesis, that means you had a type 2 error. So you definitely need to understand what type 1 and type 2 error are. And then, you know, of course, the alternative to that. So nice little table in your textbook to kind of help you out with that. So this one here is saying basically that you have made a type 1 error if the machine is not actually out of calibration. So we are saying a type 1 error has been made since the sample evidence led the quality control manager to reject the null hypotheses when the null hypothesis is true. So even though it was true, you still rejected it, and that's when we created a type 1 error. Now they're saying the management has informed the quality control department that it does not want to shut down the filling machine unless the evidence is overwhelming that the machine is out of calibration. So what level of significance would you recommend the quality control manager to use? And this one here, when we're talking about the level of significance, we're talking about what is the probability of making a type 1 error. If you increase the level of significance, it is more likely that you will end up rejecting the null hypothesis. So you kind of want to keep it at a lower end, when you're choosing the level of significance. So I would probably start out with the smallest number, 0.01, and that means that our probability of making type 1 error would be very small if you kept that level of significance at 0.01. So this one is more of a concept problem, people, than it is a calculation one, right? Because this is making sure you are understanding how to write out your null and alternative hypotheses, making sure you're understanding how the type 1 and type 2 errors work, and what that conclusion kind of leads you to. So you will see some questions like this in 10.1, and then when you get to 10.2, that's where you will actually have the calculations based on which kind of what you were seeing in this handout over here. And I do have 2 examples for this that you can actually look through in the viewing section of your D2L, section for this week. If you guys want me to work on an example from 10.2, I am happy to do that, but it is 12:15, so I didn't know if you guys wanted to stay on any longer, or can you watch the videos in the viewing section and use that? So whatever you tell me, I'm glad to stay longer and work on an example with you guys. Just for 1 week, Ali. So they will open on Monday and they will close on Sunday of next week. Okay. If you guys don't want to say, that's totally fine. It's not an obligation. Like I said, I do have some of these examples in the videos that I've posted for the homework help. So just put your answer to chat so that way I know what you guys are leaning towards. Do you want to stay for a problem, or are you okay? Okay, Rachel. All right, so let's do this. Those of you who want to stay, stay, and then those of you who want to leave, go ahead and leave. Of course, I'll be posting a recording of this also, so you can definitely come back and watch that later on. So those of you who want to stay, let's go ahead and take a look at an example from 10.2. And how about we pick something? We'll do the first one, 10.2.21. So let's take a look at that. Okay, so this one is actually problem number 7. All righty, so this one, as you can see, is talking about 20 years ago, 48% of parents of children in high school felt it was a serious problem that high school students were not being taught enough math and science. So that was 20 years ago, right? Now they're saying a recent survey found that 215 of 750 parents of high school children felt that it was a serious problem. They were not being taught enough math and science. So you're actually doing a comparison from the data 20 years ago to the recent survey. So that's the main goal of this problem. So they want to ask or see is, do parents feel differently today than they did 20 years ago? And they're asking us to use 0.01 level of significance in this case. So, again, we have to check for some of these requirements before we can get into the calculation. So we need to know if n p sub 0, 1 minus p sub 0 is going to be, greater than or equal to 10 or not. So your p sub 0 is actually going to be the, is it going to be for the recent one? Let me check that very quickly. No, so the P sub 0 is actually the original probability that's given to us, which is the 48% of the parents. So again, put that as a decimal, 0.48. The X and the N values are actually going to be from the recent survey. So that's 215 out of 750. So 215 for the X, 750 for the total parents. Okay, and then let's see, we need to check what N times P sub 0, 1 minus P sub 0 is going to be. So our N value is 750, multiply that with the 0.48, multiply that with 1 minus 0.48. And as you can see, this number came out to be larger than 10, so we are good to go, 187.2. And this is 1 decimal place. So 187.2, which is of course greater than 10. So one requirement has been met. Is our sample size greater than 5% of the population size? We're going to assume that yes, it is, that we hopefully have a large population. So this is an assumption we're going to make. The population size is less than 5%. Sorry, sample size is less than 5%. And then they didn't really tell us in the language of the problem that if this was a random sample or not. They just said 215 out of 750 parents, or 48% of the parents from the 20 years ago. So this one here, we're obviously going to say we can reasonably assume that our sample is going to be random. And so we are saying the requirements for the hypotheses are satisfied, so that we can actually do the hypothesis testing. So obviously some assumptions happening here, but these are reasonable to make. Now we actually need to come up with our null and alternative hypotheses. So here we are, obviously using percentage probability. So P is going to be our variable in this case. And then of course, for the original null hypotheses, we want to know if the probability, even now in the recent survey, is that going to stay, at 48% or 0.48. However, the question is asking us, do parents feel differently than they did 20 years ago? So they're saying feel differently. So they're not saying has the percentage increased or has the percentage decreased. They're just saying, do they feel differently? So when they're talking about differently, this one, you're definitely using the not equal to as your symbol for the alternative hypotheses. So we will say this is not equal to 0.48. So that one worked out. So just, be careful with those English terminologies and how they mean when you're setting up these null and alternative hypotheses. Okay, so now we need to calculate what our Z sub 0 or the test statistic value is going to be. So to calculate the test statistic value, we actually do need the P hat, and that's this formula right here in the center. So the P hat is actually going to be the probability based from the recent survey. So that's the 215 divided by the 750. So the new parents, what they felt about the probability, and see how small that number is, 0.28667. So just around 28, 29%, whereas you had 49%. So there's definitely a difference in that probability, between 20 years ago and now. So for the Z sub 0 or test statistic, we have P hat, so the number we just calculated, and then we are subtracting from that the original probability of 48%. And I'm actually going to put this in parentheses since you have a subtraction on the numerator, and then divide this by square root of the bottom. So that is P naught, multiply that with 1 minus P naught, and then divide that by our N value, which is 750. And that should be our square root denominator. So you can see our Z statistics is coming out to be negative 10.598. And let's see how many decimals do they want? 2 decimal places. So that'll be -10. The 8 will make the 9 go up, so it'll actually change to 0.60. 59 will become 60. So -10.60. Okay, now they're asking us to determine the critical values. And as you will see, I have included this little table over here, and it's actually given to you at the bottom of your standard normal distribution table. You will see for the hypotheses testing right here on the right-hand side. And also for your confidence intervals, you know, they've got 90, 95, 98 and 99%, what those critical values should be. And then here's your hypothesis testing based on the level of significance. And our level of significance, they told us to use 0.1 as the level of significance. So 0.1 would be this guy. When they're talking about left-tailed, that means you use the less than symbol in your alternative hypotheses. Right-tailed would be if you use the greater than symbol, and two-tailed is because we don't know if it's going to be less than or greater than, right? So the two-tailed is going to be when you use the not equal to symbol. So of course, as you can see for us, it's going to come out to be plus and minus 1.645. So that's the table you want to use. And like I said, in your little template here, I have actually copied and pasted that image. So you don't have to go, you know, find the table for this one. So here, since we are doing a 0.01, our alpha is going to be that. Of course, alpha divided by 2. And we had plus and minus, so minus 1.645 and positive 1.645. And I just again want you guys to be careful here. We are talking about the level of significance as alpha. The alpha divided by 2 is going to be if you're actually going to use the standard normal distribution table. So if for some reason you didn't remember this one and you went to the body of the table, then that's where the alpha divided by 2 will come into play. But if you use this little tiny table at the bottom and you don't mess around with the main normal distribution table, then you don't have to worry about the alpha divided by 2. All right, guys, so we have our critical values. And I think they just want us to enter. So that's going to be this one here. 1.645. They want 2 decimal places. So 1.65. Alrighty. Now they're actually going to ask you if you are going to accept or I guess reject or not reject the null hypotheses. And that's where you need to look at this little table that I've created kind of over here. So you have to look at this one here. And our numbers are actually going to be different than what I have mentioned in here. So for us, this is negative 10.598. And our z-score was actually 1.645. So what you are looking at here is basically, is your z sub 0, which is this number, less than the negative value of the alpha? So, you know, is negative 10.598 less than negative 1.645, or is your z-score greater than the positive 1? So is negative 10.598 greater than the positive number 1.645? Because didn't mean to do that. Because based on that, you have to see, are you going to reject the null hypotheses or not? So obviously we know that a negative number is not going to be greater than a positive number. So we're obviously not meeting that requirement. But is negative 10 smaller than negative 1? Yeah, it is, right? Because on the negative side of the number line, as you go further left, the numbers get smaller. So yes, because this is true, because we can say yes, -10 is smaller than -1.645, we can reject the null hypotheses. So we are meeting this requirement, -10,598. Yeah. So you can go ahead and reject your null hypotheses. So coming back to our this one here, now which option is it going to be, A or B? Because they are saying reject the null hypotheses for both, but then they say there is insufficient evidence to conclude that the number of parents who feel that students are not being taught enough math and science is significantly different from 20 years ago. So is there insufficient evidence, or do we have sufficient evidence that the number of parents who feel differently from 20 years ago to now, you know, that students are being taught math and science, are not being taught math and science? And for that, I would say look at the two probability values, the p sub 0 and the p hat that we calculated. Do we have sufficient evidence or do we not have sufficient evidence? So is it going to be part A or part B? Because, you know, of course, we know it's not going to be C and D because we are rejecting the null hypotheses. So those two options are out. So it's between A and B. Go ahead and put your answers in the chat. Just put A or B. Let me see what you guys are kind of thinking so I know if you are understanding this example or not. Ian, okay. Lourdes, Rachel, it's okay if you're, you know, not sure. Just put one answer that you think you would go with. Okay. And Lourdes, what about you? Okay. So when you look at the two probabilities over here, you can see that back 20 years ago, we had 48% of the parents who thought the kids are not being taught, you know, math and science. Now it's about 28, 29%. So there is actually significant difference between how the parents felt back then to what they are feeling right now. So we will actually say that actually we do have sufficient evidence that parents feel differently then and now. So that is going to be your option. So that is a sufficient evidence for us. And then, you know, of course, based on what our critical value came out to be with the test statistics, you are able to compare if you need to reject or not reject your null hypotheses. So that's one example for you guys to look through in 10.2. I would definitely ask you guys to work through the 10.27 example in the viewing section of the D2L for this week, because this one is not a big problem. It just has a couple different calculations as part of it. So don't get you know, overwhelmed by looking at all the different things that are here. It's just there's two parts because you're doing, you know, comparisons. And so it just comes out to be a little bit different over here. So just look through this video, and if you have, you know, any questions, obviously let me know. So all of that is available for you under the viewing, and you can see there are a lot more examples under the view section than we were able to cover in class. So hopefully you guys will be able to, you know, look through these examples and work some of these out. And I will be here this week. So if you guys have any questions, please don't hesitate to reach out, and I'll be happy to help you out with anything you get stuck on. So again, guys, don't forget to request your password if you haven't done so already. And then I will see you next week. Just keep in mind, Monday, I will open up the older homework assignment so you can work on anything from chapter 1 to chapter 10 next week. But my recommendation would be get chapters 11 and 4 completed first, and then go back and work on anything old, because you don't get to retake 11 and 4. That's just, you know, whatever you do next week. And then you can work on anything from 1 through 10. Okay. So if you want to stay back and ask any more questions, guys, I'll be happy to do that. And if not, I will see you next week. So be careful, everyone. Stay safe. Have a wonderful week.
Thank you.
Thank you.
Yeah, guys. Okay.